Okay, this is a continuation of composition of transformations. The next composition of transformations we're going to learn is the glide reflection. And you can see that there are two words here, glide and reflection. So a glide reflection is a composition of a translation or a glide or a slide and a reflection across a line parallel to the direction of the translation. This is very important. The fact that we are reflecting across a line that is parallel to the direction of the translation. That is not just incidental, that is important. So let's put your player on pause and let's take this down. You do not need to copy the picture of the helmet. Okay, so what is actually happening? I'm taking ABC. I'm going to start off with this image right here, ABC. A being the face guard of the helmet, B being the top, and C being the back of the helmet. I'm doing a translation, which is a slide, of my helmet to this point over here, and then I'm reflecting it over this line. I'll call this line L1. So again, I'm starting off here, ABC. I am sliding the helmet, and look at the direction I'm sliding it. I'm sliding it parallel to the line I'm eventually going to be reflecting over. And when I do my reflection, I end up with A prime, B prime, C prime. So that is what a glide reflection is. It is a glide or a slide parallel to the line that I'm eventually going to be reflecting over, which is L1. So here's the question. Is a glide reflection an isometry? And does a glide reflection preserve orientation? So see if you can figure this out for yourself. Put your player on pause, see if you can come up with an answer in your head, and we'll see if your answer is the same as ours. And then you can play resume. Okay, so is a glide reflection an isometry? Well, here's the question. Is a translation an isometry? And is a reflection an isometry? And the answer to both is yes, because a slide or a glide or a translation does not change size or shape. Remember, an isometry is a transformation where size and shape stay the same. Isometry means that nothing changes about the pre-image and the image in terms of its size and shape. And it's true. A translation does not change the size and shape of the helmet. Nor does a reflection. When you look in a mirror, you do not see a larger or smaller image of yourself. So therefore, does a glide reflection maintain isometry? Is it an isometry? The answer is yes. Now, does a glide reflection preserve orientation? Well, let's ask the question this way. Does a translation preserve orientation? And the answer is yes. As you can see, ABC is in a counterclockwise direction. And once I do my slide, that's in a counterclockwise direction. However, when I reflect over the line L1, my orientation changes. Notice how I was going in a counterclockwise direction. After the reflection, I'm going in a clockwise direction. So the answer is no, it does not, because a glide reflection is made up of a glide plus a reflection. And because a reflection does not preserve orientation, a glide reflection does not either. So let's put this down in our notes. How else can I do a glide reflection? So here's an example where I take ABC and I do the glide parallel to my line of reflection, and then I reflect it over L, my line of reflection, and I end up with A prime, B prime, C prime. How else could I have done this glide reflection? Suppose I had done the reflection first and then the glide. So in other words, suppose I had just first reflected ABC in my line of reflection and gotten ABC here, and then I did my glide afterwards. Would it end up in the same place? Yes, it would. So in other words, a glide reflection can be reversed in terms of its order. So a glide reflection is commutative. So please take this down. This is an important rule. A glide reflection is a commutative composition of functions. A glide reflection is commutative. Okay, let's take a look at the next rule. And here we go. Suppose I want to do two reflections. I want to compose two reflections across two parallel lines. What do I end up getting? In other words, if I have a reflection over two lines that are parallel to each other, I'll call this line L and I'll call this line M. I first reflect over line L. So let's actually give these labels. So I have A, B, C. right? So A maps to A prime after my reflection, B maps to B prime after my reflection, and C maps to C prime after my reflection. After I do this initial reflection over line L, I'm then going to take A prime, B prime, C prime and reflect that over line M. So what do I get? I get A double prime, and I get C double prime here, and I get B double prime there. Okay. One thing you have to remember is the distance from the pre-image to the image is the same. The distance of the pre-image to the image is the same, right? So we cannot forget those rules. Those are important. Okay, so now what I'm doing is I am now reflecting the A prime, B prime, C prime over line M, and I get A double prime, B double prime, C double prime. What type of transformation is that identical to? Well, if you'll notice, if I take triangle ABC and I simply slide it down to A double prime, B double prime, C double prime, I've basically done a translation. You'll see that it is a translation. So when you reflect over two parallel lines, when your composition of reflections is over two parallel lines, that is the same thing as a translation. So let's take that down in our notes. A composition of reflections across two parallel lines is a translation. That is rule number 4 of composition of functions. You can take down the diagram as well. That will help you remember it. Put your player on pause if you need to. Okay, next one. Suppose the lines that I'm reflecting across are not parallel. Suppose they intersect. So here's an example of, I'm going to start off with this triangle right over here, which is A, B, C. And I'm doing a reflection. So this is A prime, this is B prime, and this is C prime. And now I'm going to do another reflection over not two parallel lines, but two intersecting lines. So this is line M, this is line M. So reflecting ABC over line L gives me A prime, B prime, C prime. And then reflecting A prime, B prime, C prime across line M gives me, let's see if I can do this, B double prime is here, C double prime is here, and A double prime is here. So what kind of transformation is that identical to? Well, I'm going to try to do something. Let's see if this works. If I take this image and, whoops, and I rotate that, you'll notice that that fits nice and snugly into A double prime, B double prime, C double prime. So it looks as if, and let's see if we can play this back again. There we go. So basically, reflections over two intersecting lines is the same thing as a rotation. So this is rule number 5. Please take this down. A composition of reflections across two intersecting lines is a rotation. You can try to take down the diagram. That might help you understand it better as well. Put your player on pause and hit play to resume. Okay, last rule. Here we go. The last rule is as follows. If the coordinates of point P, 2, minus 3, are first rotated 180 degrees counterclockwise and then rotated 90 degrees counterclockwise after that, what is the image of P? So first, when I rotate 2 minus 3, 180 degrees counterclockwise. So if you don't recall, so 2 minus 3 is roughly over here, 2 minus 3. When I rotate 180 degrees counterclockwise, this is 90, this is 180, and then if I take that result and I rotate it 90 degrees more, altogether I've rotated 270 degrees. So what I could do is I can simply add 180 and 90. Whoops. What I can simply do is add 180 degrees plus 90 degrees to get to 270 degrees. So basically a rotation of 90 after a rotation of 180 is identical to, a rotation of 270 degrees. I can also call a rotation of 270 degrees counterclockwise. I can also call that a clockwise rotation. I can call that a clockwise rotation, which I will do in green, of 90 degrees. Remember, clockwise is negative. So what I can do is I can think of 2 minus 3 being rotated clockwise 90 degrees, or I can think of it as being rotated counterclockwise 270 degrees. And of course, what's going to happen is I'm going to take my x and y values, I'm going to flip them, and because I'm in quadrant number 3, both the signs of x and y are negative, so my answer is going to be -3, -2. So how can I express the following composite transformations as one transformation? Very simply, I can express it as one transformation either as a rotation of 270 degrees clockwise, or I can express it as a rotation of 90 degrees counterclockwise. So a composition of two rotations is a rotation. So let's take down rule number 6 and then try to do the next piece. Find P prime, the image of P, -4, -5, after a rotation clockwise of 90 degrees after you've first gone 270 degrees. So first, let's come up with a rule. So the rule would be what? Let's first add 270 and 90. So if I take the rotation of 270 clockwise and I add to that the rule of 90 degrees, sorry, 270 degrees counterclockwise, and I add to that the rule of going 90 degrees clockwise, what I've basically done is I've gone 180 degrees clockwise and 180 degree counterclockwise. And 180 degree counterclockwise rotation, because this by default is positive, is the same thing as doing a rotation of 180 degrees counterclockwise, because it's going to leave you at the same point. So basically I'm doing a rotation of 180 degrees counterclockwise on what point? -4, -5. So if you're not sure what that looks like, -4, -5 is roughly down here. That is point P, -4, -5, -4, -5. I'm rotating that 180 degrees, whether I go counterclockwise or I go clockwise. What's going to happen is I'm going to flip my xy values twice, but now both x and y in quadrant 1 are positive. So my answer is going to be 4, 5. And if you got that, a check for you.